Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome back. Today we are going to talk about index properties of rock and rock mass. Before we get on with today's subject, we are going to consider the questions that I gave you in the last presentation. The first question that was asked was how fine and coarse grained soils are classified. So, basically classification of fine grained soils and coarse grained soils have to consider the facts that these soils, the behavior of these soils are primarily governed by plasticity and grain interlocking or grain size respectively. As a result, for classification, the main classification of fine grained soils, the main consideration is the liquid limit and the plasticity index. And we go into the Casagrande chart, and the areas that is divided by this chart is subdivided again, as I was explaining in the last presentation. Let me repeat what I said. So, let us say this is the standard Casagrande plot. What you got here is a plot of liquid limit versus the plasticity index, and you have got a diagonal line, sort of a diagonal line, that is called Casagrande's A line, and this in turn is, these zones are again subdivided by drawing vertical lines at liquid limits of 35 and 50%. This is actually according to the Indian standard classification system. In case of the ASTM standard, the line at 50% is not there. So, what you got here is basic one of these lines is not there in case of the ASTM standard. Now, what you do, and also there is another subzone near the bottom left of this particular plot, which is reserved for a category called CLML. Then what we got is basically this one is O. This area is reserved for MH or OH type of soils. Then this one is MI or OI. Then here we have got ML or OL. Top left we have got CL. Then we have got CI, and finally on the top right we have got CH. So, this is the Indian standard classification chart for fine grained soils. Okay, now let us get back. How did we classify coarse grained soils? In classification of coarse grained soils, what we looked at is the grain size of these type of soils, and we considered only those soils which have more than 50% of coarse grained particles, that is particles that are coarser than sand size particles or coarser, that means the particles which are retained on sieve of opening size of 0.075 millimeter, and then these type of soils, so 50% of the total weight of the soil will be composed of grain size of sand size or coarser, and then there were two subcategories of this type of soils. In one of these subcategories, more than 50% of the soil is composed of gravel size particles, and as you recall from previous day's lesson, gravel size particles are those particles which are retained on mesh or sieve size of opening of 4.75 millimeter, and if more than 50% of the soil is composed of sand size particles, then they are called sands. And so what we got here is again, so this is for coarse grained soils, so we can have gravels, and these type of soils have got several different classes like well graded gravel, poorly graded gravel, silty gravel or clayey gravel. Then you have got sand. In case the particles more than 50% by weight of the soil particles are composed of sand size particles, then these things are also have got four subcategories: well graded sand, poorly graded sand, silty sand and clay sand. So that is in a nutshell the procedure used in the Indian standard classification system of for classifying fine grained and coarse grained soils. Okay, the second question what I gave you was I asked you to find the moisture content for a saturated sample of soil if the specific gravity of the soil solids is 2.7 and the porosity is 0.4. Okay, let's get back to the tablet. So what is we have to convert porosity to void ratio. So we know that that void ratio E is given by n over 1 minus n. So n in this case is equal to 0.4. So what we got here then is a void ratio of 0.4 over 0.6, that is equal to 0.67. Okay, now you recall see what we have to show here is an actually what we have to calculate now is the moisture content. So you recall in the last day's presentation we used an identity given by this saturation ratio multiplied by the void ratio is equal to the moisture content multiplied by the specific gravity of solids. So that gives us what? W is equal to G divided by SR, W is going to be given by just the inverse of that really. So W is going to be given by saturation ratio multiplied by the void ratio divided by the specific gravity of solids. We know in this case saturation ratio is 1 because the sample is completely saturated. So our water content or moisture content will be given by the void ratio divided by the specific gravity of solids, that is 0.67 divided by 2.7, which is going to be approximately equal to 24.7%. We multiplied it by 100 and we express the moisture content in this case in percentage. Okay, so that is the second solution. And then the third question that I asked you was to prove the identity that gamma dry is equal to gamma bulk over 1 plus W. And let us look at the proof. You remember moisture content is given by weight of water divided by weight of solids. So that gives us 1 plus W equal to W plus Ws divided by Ws. That means the total weight of the three phase material divided by Ws. That is in turn going to be giving us Ws. This is big W, actually Ws is going to be equal to capital W, that is the weight of the entire three phase soil sample divided by 1 plus the moisture content. Now gamma dry is equal to weight of solids divided by the total volume of the three phase material. So that using the result that we just now derived is going to be W, capital W. Capital W is the weight of the entire soil specimen divided by 1 plus the moisture content small w multiplied by V, and we know that capital W by capital V is equal to gamma, that is the bulk unit weight, that can be replaced by gamma, and what we are left with in the denominator is 1 plus W. So that is the identity that I asked you to prove then. So in this case gamma dry is equal to the bulk unit weight divided by the 1 plus the moisture content. Gamma dry in this case is the dry unit weight, and all other terms used in this derivation is explained. Okay. Then the fourth question that I asked was qualitatively what is the difference between two samples classified as SW and SM. So the crux of the matter in this case is that both of these specimens, they are going to have representation of a large range of grain sizes, but the difference between SW and SM is essentially that SW, well graded sand, it has got very minor amount of fines present. So it is basically a type of clean sand, whereas SM is the designation used to denote silty sand, which has got quite a few tens of percents of silt size particles present within the matrix. Okay, so that takes care of the questions of the previous lesson. Now we move on to the subject matter of today's lesson. So we begin with the objectives of this lesson, what we want to learn from this particular lesson. We are going to learn the factor, we are going to list, we should be able to list the factors, main factors that govern the engineering behavior of intact rock specimens and rock masses. Then we should be able to estimate some indices that govern these behaviors, and using this insight we are going to be able to classify rock masses. Okay, so that actually is the those are the objectives of this particular lesson. Now let us try to understand what is that we mean in engineering sense by the term rock. Now if you recall from our earlier lessons that rock, there is a fuzzy line that separates rock from soil, in the sense that some soils could be could be stronger in fact than some weaker varieties of rock. So, there is really a fuzzy line that separates rocks from soil. So, what we tried to do earlier in order to differentiate the notions of rock and soil is that we said that soils are in a sense assemblage of mineral or organic material, decomposed organic material, just like rock, but the difference between rock and soil is in the fact that individual particles that compose soil samples, they can be relatively easily separated from each other. So, for example, if we take a sample of soil and if we take it, if we mix it up with a little bit of water and we try to put it in a blender and stir it vigorously, and what we are going to end up with is that all the individual soil particles, they are going to get separated from each other. But that is not going to happen if we do the same thing with a small piece of rock. So, the essential difference then is that rock mineral particles that compose a mass of rock, they are stuck together by a much stronger bond in comparison with individual soil particles. So, it is the individual rock particles, they are much difficult to separate from each other. So, that is the essential difference. Now, it is a qualitative statement really, and there is no sacrosanct line or quantifiable line that separates the material what could be termed as rock from what could be termed as soil. And this actually gives rise to a lot of construction dispute if the construction contract is not properly worded. Now, anyway, so we then know that what is rock? Rock is essentially a natural aggregation of mineral, and this aggregation is usually cemented, and as I explained that the bond of cementation is much stronger in this case in comparison with most of the soils. Then the aggregation is more compact than the soil. That means the porosity of a rock mass is much smaller in comparison with that you would expect in case of a soil sample. Then rock mass also, I mean, if you consider a relatively large volume of rock, then you are likely to see some discontinuities within the rock mass, and rock is expected to occur in various states of weathering. So, this is actually a very qualitative description of the notion that is alluded by the term rock. Then what is the second bullet? The second bullet follows essentially from the first bullet, in that rock mass response is controlled by the characteristics of both the mineral aggregation as well as the properties of the discontinuities. So, what we if we want to see the engineering behavior of rock, then we have to look at the engineering characteristics of the intact specimen of rock that is bounded by the discontinuities, as well as the properties or the characteristics of the discontinuities themselves. So, this is going to be a rather challenging job in comparison with soils, because you remember that in case of soils, we actually we were describing the properties of the three-phase material, considering the soil to be a continuum, not unlike in this case where the mass is actually crisscrossed by discontinuities. So, that is the basic difference that we will face when we are trying to look at the engineering characteristics of rock. Now, first of all, we have to look at the strength. The first step in trying to characterize the rock, I mean the engineering behavior of rock mass, we are going to try to characterize the properties of intact rock specimens, and the first thing that comes to mind is how you are going to characterize the strength of an intact rock specimen. So, what we do typically, the easiest option is to conduct a uniaxial compression test, in which we have got a core sample with a cylindrical sample of rock really that is subjected to an axial compression. So, the sample of rock in this case in this cartoon is shown with a brown rectangle on the left side of this particular slide, and then what we are going to do, we are going to keep track of the deformation of this particular sample and the corresponding value of the axial force or axial stress, and we are going to express the result as a plot between the axial stress and the axial strain. You all know that axial stress in this case is going to be the axial force divided by the cross sectional area of the specimen, and axial strain in this case is going to be the deformation in the axial direction divided by the undeformed length, undeformed axial length of the specimen. So, let us begin the test. So, first of all, we apply a small load, small axial load, compressive load on the specimen, and as a result the length of the specimen is going to shorten a little bit, and we are going to plot that particular value, corresponding value of the axial stress versus the axial strain. And you look at the plot to your right, and you are going to see the stress strain curve is going to gradually develop as we apply larger and larger amount of deformation on the sample. Okay, so we increase the axial load, and what we get is further shortening of the sample, and we as a result we get a longer plot of the axial stress versus axial strain. Continue the test. The sample shortens further, and it shortens further, the stress increases more, stress goes up even further, and you can see that the stress strain curve is trying to bend over to your right. So, this is a nonlinear stress strain response that we are looking at in this case, and then what we are going to get, the stress strain curve is going to bend further over, and it is going to become almost horizontal with no further increase in the stress possible, and this particular situation is actually, it corresponds to development of damage within the sample, because the sample is going to get damaged as deformation increases, and cracks are likely to develop within the sample, and as a result we might get a reduction in the strength, as you are going to see in the next little bit. So, if we try to deform the sample further, what we will see is that the stress does not go up anymore, because the sample starts to crack up, as is shown by the dark lines going across the shortened specimen on your left, and if we try to strain the sample even further, then these cracks, they are going to actually propagate further, and the strength of the sample is going to decrease even further, and ultimately what is going to happen, the sample is going to split up, and that is going to be the ultimate failure state of this particular specimen. So, that is how the unconfined compression test is carried out, and the strength that we obtain in this particular test is called the unconfined compressive strength, or the UCS. And if you look at the slide there, the UCS for this particular specimen is marked on the slide, on the plot to the right of the slide there. Okay. So, then let us move on and let us try to see the sequence once again. So, in this case I am just going to run the animation, and you just try to observe the shortening of this particular of the sample that we are trying to test here, and how the cracks develop within the sample, and the sample goes to the ultimate state of failure. Okay. So, here you go. So, that is how the UCS is conducted. So, here why this particular test is called unconfined is because we just apply axial stress in this case, or axial deformation in this case, and we do not make any attempt in this case to confine the sample in the lateral direction, or we do not have any confining pressure that actually keeps the sample from bulging in the lateral direction. So, that is how the unconfined compression test is conducted. Okay. Now, there is a simpler method for finding out the unconfined compressive strength of a specimen of intact rock, and that particular procedure is called a point load test. So, what is done in this case? We are going to take a core sample. You remember that a rock core sample is going to be approximately cylindrical, and we are going to only choose those samples which have a length of at least 1.5 times its diameter, and then we are going to apply a point load diametrically across the specimen, and then we are going to calculate a term called the point load index, and that point load index is going to be converted to the unconfined compressive strength of the specimen by the equation that is shown near the bottom of this particular slide. Now, here the point load index is this term, is the term on the right there. So, P here, the uppercase P here is used to denote the load, the point load that splits the core sample, that splits the sample, and D here is the diameter of the core sample. D is the diameter of the core sample. So, in other words, the point load index is given by P over square of D. Now, this particular equation, for using this particular equation, you have to use D in millimeter, and if you do that, and if you take P in Newton, then you are going to compute the UCS value in MPa or in Newton per square millimeter. So, you have to remember that you can only use this particular equation if you have D, the diameter of the core specimen, in millimeter, and the force that splits the sample in Newton. So, the equation then is UCS is equal to 14 plus 0.175 D multiplied by the point load index, and point load index is given by P over D square. Okay. So, the schematic of this particular test, point load index point load test, is shown here. So, what you see here are basically the rock core that is noted there, and then point load is applying using two sharp points. So, these are the points across which the core sample is mounted, and these two points are actually brought near to each other. They are brought near to each other, and that in that process the rock sample, I mean, it tries to squeeze the rock sample, and a tension develops across the sample, and that ends up splitting the sample in the lateral direction. So, that is how this particular test is conducted. That is the schematic details of point load testing. Okay. Now, we want to classify rock samples, intact rock samples, depending on their unconfined compressive strength. If you have got an unconfined compressive strength of between 1 and 25 megapascal, then you are going to call that particular rock or classify that particular rock as very low strength rock. Examples of this particular category is are the rocks are chalks and rock salt. Then you could have low strength rock with UCS between 25 and 50 megapascal. Examples include coal, siltstone and schist. Medium strength rock, if you have got unconfined compressive strength of between 50 and 100 MPa of an intact specimen. Examples are sandstone, slate and shale. You could have high strength rock if the unconfined compressive strength goes between 100 and 200 MPa. Examples being marble, granite and gneiss. And finally, very high strength rock if you have got unconfined compressive strength of more than 200 MPa. So, this one is in MPa, this one is in MPa, just like before. Examples are quartzite and basalt. Okay, so that is how you are going to actually classify intact specimen of rock based on their unconfined compressive strength. Now, we know that characterization of intact specimen is only only about half of the total problem, because we have to now categorize or characterize the discontinuities in terms of their behavior and strength. So, what we mean by discontinuities, they could be of different types, and all of them, many of them have already been discussed when we were talking about different types of rocks. The first type of discontinuity belong to the category of bedding planes and foliation. So, you remember in case of gneiss or schists, what we had is basically relatively thin lamination of alternate layers of different minerals. So, this kind of stacking is called foliation, and you can have bedding planes in case of sedimentary rocks, and we discussed the details or details of the geometry of these characteristics. And then we can have folds. So, what we mean by folds is basically, let's say you have got a rock mass which has got horizontal bedding like that, and this particular rock mass is subjected to a compressive load in the lateral direction. Then what is going to happen is that the bedding, they are going to bulge up in this manner, and finally what you could get is a rock mass that has got bedding planes of this type. And we discussed these features in details in greater detail when we were talking about different types of faults and folds in one of the earlier lessons. Okay, so that is what is fold. Then you could have joints. So what are joints? Joints are basically static discontinuities. Joints basically are static discontinuities. That means let us say you are for a volcanic rock is being formed, and when the magma cools, then different parts of magma solidifies at different rates, and as a result the magma could shrink, and that leads to the development of joints within the mass of cooling magma, and these joints, they remain within the body of rock, and this particular type of discontinuity is given the name joints. So joint are essentially static discontinuities in the sense that basically they are not because of relative movement of different parts of the rock mass. So we talked about different joint sets because in our earlier lessons we talked about columnar basalts and pillow basalts. So you could have basalt columns developing in this manner, because of differential cooling within different portions of the magma. So in this case these features are called joints. So these are the joints, and this is an example of joints for a type of rock called columnar basalt. Okay. Then finally we have got fractures. We can have fractures. These are also discontinuities, but in this case, unlike joints, some dynamic trigger is involved in the development of these discontinuities, and fractures develop because of relative movement of different parts of the rock mass, and there are two subcategories of fractures. One is called shear zone and another one is called fault. Shear zone, when the movement is relatively of small magnitude, the permanent slip between different portions of the rock mass is of smaller magnitude, then the discontinuities that result from that kind of movement is called shear zone. If the movement is much larger, then we could have that leads to the development of faults, and we looked at various different categories of faults in our earlier lessons. Okay. So now the question comes, how we are going to characterize discontinuities. So discontinuities could be continuous or discontinuous. That means the discontinuities themselves can go a larger distance, or they could be confined within a relatively small volume of the rock. Then the walls of the discontinuity could be rough or smooth. They could be fresh or weathered, or in other words, the wall themselves could be hard, or they could be soft because of the weathering action. Then discontinuities could be welded, or they could be clean or infilled. What we mean by welded is that within these discontinuities, chemical or other minerals, they get deposited, and these deposits, they act as a welding agent connecting the two blocks that are on either side of the discontinuity. So, welded discontinuity is going to be much stronger in comparison with discontinuities that are not welded. Then discontinuities could be clean, or they could be infilled with weathering material or other types of deposits, unlithified deposits, or deposits that are not that are yet to turn into rock. Then the composition of the infill could be they are most of the time they are composed of different types of clays, because if you recall from the discussion that we had earlier on chemical weathering of rock minerals, they get weathered and that leads to the formation of clay minerals, different types of clay minerals, and these clay minerals actually fill the discontinuity, because the weathering action is also going to be more pronounced across at the discontinuities themselves, because of water entry and entry of air and so on and so forth. So, these discontinuities sometimes get filled by clay type minerals, and these clay minerals could be either swelling type clay or just like smectite, or they could be inactive clay minerals such as kaolinite, or the discontinuity could be filled with rock flour. They are basically particles, non-clay particles. They are fragments ground up from the relative movement of the two parts of the rock across the discontinuity itself, and that also could be another type of infill material within the discontinuity. Okay, so we have to consider all these aspects when we try to look at the behavior of discontinuity. Now, we try to look at an index of discontinuity spacing. So, two indices we are going to look at in this case. One is called the recovery ratio, and the other one is called the RQD, or the rock quality designation. How do you define RQD? RQD is the ratio of the length of core pieces, of the pieces of core, individual length of which is equal to or more than 100 millimeter, and that is divided by the length of the core run. Once again, RQD is given by the length of pieces of a core specimen which are more than 4 inches long, 100 millimeter long, and we are going to divide that, the cumulative length of those pieces which are more than 100 millimeter long, by the length of the entire core run. Now, RQD is typically expressed only for cores that are more than or equal to 54.7 millimeter diameter, drilled with double tube core barrel. Then recovery ratio, the second index, is given by the length of the core recovered divided by the length of the core run. So, in this case, let us consider the core sample near the bottom of this particular slide. So, here let us say we have got more than, I mean this particular core piece is more than 100 millimeter long. Then let us say this particular core piece of core sample is also more than 100 millimeter long. Then there is another long core piece that is this much out here, and we have got another one which is out here. So, what is going to be the RQD in this case? Let us call this one L1, this one L2, then the third piece as L3, and the fourth one is L4, and the core run in this case, let us express that by the symbol R. So, what we are going to get in this case, RQD is going to be equal to L1 plus L2 plus L3 plus L4, and this entire thing is going to be divided by R, and this particular ratio is oftentimes expressed as a percentage. Okay. Then let us consider for this sample itself how we are going to express the recovery. So, recovery in this case is going to be given by the length of the core recovered, that in this case is this much, and that is going to be divided by the length of the core run. So, recovery here is going to be given by L over R, and this in turn is going to be expressed by percentage. So, we are going to multiply L by R by 100 and express core recovery by percentage. So, both RQD and recovery, if you recall, when we discussed the logging activity of subsurface investigation, both RQD and recovery are details that needs to be included in the log that describes the drilling process, and they are evaluated at the time of the drilling itself. Okay. Now, we will try to get into the geomechanics classification of rock mass. So, first of all, we are going to consider the UCS, unconfined compressive strength of the rock mass, and we are going to assign a score R1 depending on what is the value of the unconfined compressive strength of intact specimen of rock. So, if it is for instance more than 200 MPa, then we are going to have an R1 of 15. If we have let us say UCS of between 50 and 100 MPa, then the R1 reduces to 7. Second aspect to consider is the RQD of the core sample, and we are going to assign a score of R2 depending on the RQD. For instance, if RQD is between 90 and 100, then score R2 is going to be 20, whereas if RQD goes to between 25 and 50%, then R2 becomes equal to 8. Third aspect to consider is the joint spacing, and the score in this for this particular aspect is R3, and here if the joint spacing is more than 3 meters, that the joints are very widely apart, then R3 is going to be equal to 30, whereas when the joints are between 50 millimeter and 0.3 of a meter, then R3 will be equal to 10. There are further aspects to consider: joint condition, and the score that are going to be assigned, score that is going to be assigned to characterize joint condition is going to be R4. In this case, if we have got very rough joint with hard wall that are discontinuous and there is no separation of the rock blocks across the joint mass, that the separation is less than say 1 millimeter, then R4 is going to be equal to 25. If the joint on the other hand is filled with soft clay like gouge is the term used for joint infill, and the joints are continuous, and there is more than 5 millimeter separation of the rock body of the rock blocks across the joint, then R4 is going to be equal to 0. Then the fifth aspect that we are going to consider is groundwater. If the rock mass is dry, then R5, the score that characterize the groundwater condition, is going to be 10. If the rock mass is moist, then R5 is going to be equal to 7. If there is moderate pressure in the groundwater within the rock mass, then R5 is is going to be equal to 4, and in case of severe inflow of groundwater, R5 is going to be equal to 0. And finally, we have to consider joint orientation with respect to the project vis-a-vis the project that we are handling, and the score that we are going to consider to account for this aspect is R6, and it is going to be different if we are looking at tunnel construction, or if we are looking at construction of a foundation or construction of a slope. If the joint orientation is very favorable, then R6 is going to be 0 in all cases. If the joint orientation is very unfavorable, in case of tunnels, we are going to have a negative 12 for R6. In case of foundation, we are going to have negative 25, and in case of R6, in case of slopes, we are going to have negative 60. Then what we do is we sum up all the R values, all the ratings or all the scores R1 through R6, and the sum is given the name as rock mass rating. If the rock mass, or RMR actually, rock mass rating or RMR. So, if RMR is between 100 and 81, then the rock class is 1. If RMR goes to between 41 and 60, then rock class is 3. If on the other hand RMR is less than 20, then rock class is 5. And you can easily intuitively see that the strength of rock mass is going to be very high if you have got an RMR of between 100 and 81. If you have got a class 3 rock, the strength is going to be moderate, intermediate, and if you have got class 5 rock, then the strength of the rock mass is going to be very low. At this time, we are not going to consider the correlations between RMR and the design strength of rock, but you should be aware that those kind of correlations are available, and we are going to consider those correlations connecting the rock mass rating and the shear strength of rock later on in one of the future presentations. Okay. What we learnt in this particular lesson, we looked at the fundamental factors that affect the engineering behavior of intact rock and rock mass. We considered indices of engineering behavior of intact rock and rock mass. For example, we looked at RQD, we looked at the UCS, we looked at the recovery ratio. They were the indices that we considered in order to describe the behavior, engineering behavior of the intact specimen as well as the mass, a jointed rock mass. And we also looked at some of the procedures that are used for estimating these indices. Okay. In order to wrap up this particular lesson, I am going to leave you with a number of questions. First of all, you try to answer these questions at your leisure, and I am going to give you my answers when we meet again in the next lesson. The first question is, what are the differences between joints and fractures? Second question, is a sandstone core sample of 55 millimeter diameter failed in a point load test at 17,000 meganewton force, and you are asked to estimate the unconfined compressive strength of that core sample of the intact rock. The third question is, classify the following granite rock mass for a tunnel construction, and the given parameters are UCS equal to 150 MPa, RQD is equal to 70%, joints are with rough surfaces, joints have got rough surfaces and hard wall, and the spacing between individual joints is 0.5 meter, and the separation of the blocks of rock across the joints is less than 1 millimeter. Now, this particular rock mass contains groundwater under moderate pressure, and the joint orientation is fair with respect to the tunnel alignment. So, you try to answer these questions following the procedure that has been described in this lesson, and when we meet again we will take up these questions and consider the answers. So, thank you very much and bye for now. Hello everyone, and welcome back. Today we are going to learn about stress strain behavior of soil and rock. But before we take on the subject matter of today's lesson, we are going to look at the question set of the previous lesson. And this is the question set. The first question was, what are the differences between joints and fractures? So, by joints, what I meant was there is no dynamic movement is responsible for the discontinuity, whereas in case of fractures there is a relative motion between the blocks on either side of the discontinuity. So, joints for instance could arise because of the differential cooling of the original rock forming material, semi-solid rock forming material or magma, and because of that there might have been cracking within the body of the semi-solid object, and these things remain in the rock mass, and these features we are going to call by the keyword joint, whereas fractures develops later on during the lifetime of the rock mass because of relative movement between different portions within the rock mass. So, that is the essential difference between joints and fractures. Then the second question that I asked was, a sandstone core sample of 55 millimeter diameter failed in a point load test at 17,000 meganewton force, estimate the UCS. So, the problem here is like this. We have got a core sample, and that core sample has got a diameter of 55 millimeter, and this particular core sample was subjected to a point load test, and when P became equal to 17,000 meganewton, this particular core cracked. So, this is the problem, and based on this data set we are going to